Now that we have defined the probability density function and the cumulative distribution function, let's consider our first branch of distributions, namely discrete distributions. The binomial is used for discrete data. It is one of the most widely used discrete distributions. The binomial is best applied when the sample size is less than 10% of the population. When we sample using the binomial sampling, we must have replacement. Although binomial has a constant success rate, it can be used in defect probabilities when the proportion defective is equal to or greater than 0.1. Binomial can be approximated to other distributions. This is one reason it is so frequently used. It can be modeled to the discrete distribution known as Poisson if p is less than 0.1 and the sample size is large. It is also an approximation for the hypergeometric distribution as the sample size becomes large and the proportion of successes approaches a constant value. When n times p is greater than or equal to 5, the binomial can be approximated to the normal distribution as shown in the visual on the left. As n gets larger, the alignment between the binomial and the normal becomes stronger. The PDF for the binomial is given in the upper right corner of this slide. Note that all combinations of success must be accounted for in each probability calculation. This is the portion of the formula with factorials. The mean is just the product of the sample size and the success rate. Standard deviation is the square root of the product of the sample size, success rate, and failure rate given by 1 minus p. The binomial distribution requires situations with only two outcomes. The number of trials is finite and independent. There is a constant success rate. Let's consider this binomial problem. Since there are 4 choices, the success rate is 0.25. N is 20 since there are 20 questions. All correct means that x equals 20, and this gives us a very small probability. Note that this is not absolute 0. None correct means x equals 0. So we get 0.00317. If we make a binomial table for this problem, we see that x equals 5 gives us the highest probability of about 20%. The Poisson is another discrete distribution. It can be used to model a number of occurrences over a fixed interval of length, time, or area. For a random variable to be Poisson distributed, the probability of an occurrence in an interval must be proportional to the length of the interval, and the number of occurrences per interval must be independent. As mentioned earlier, Poisson can be approximated to the binomial when success rate is less than 0.1 and the sample size is large. The mean is just the product of the sample size and success rate. However, standard deviation is the square root of the mean. Now let's look at this Poisson problem. The mean is given as 18 customers per hour. Using technology and our understanding of probability, we can get these responses. Exactly 20 means equal to 20, and this is 0.079804. At most 20 means the probabilities of 0 through 20 added up. This gives us 0.7307. More than 20 can be found by using the complement rule. We know that probability of more than 20 is equal to 1 minus probability of at most 20, which gives us 0.2693. The probability of no customers is x equals 0, which gives an extremely small sample probability of 1.523 times 10 to the negative 8. The hypergeometric distribution is used to model discrete data. As you can see from the calculation, it consists of a series of combination calculations. Technology is best utilized. The hypergeometric distribution applies when the population size is small compared to the sample size. Unlike the binomial, the hypergeometric distribution is used when there is no replacement. Both distributions require two possible outcomes on each trial. The difference is that the binomial requires the probability of success to be the same for all trials, while the hypergeometric distribution does not. Take note of how the distribution changes in the visual as the number of successes and sample size gets closer to the population size. Consider this example. Population size, capital N, is 30. Sample size, small n, is 20. Number of occurrences in the population, D, is 10. Number of occurrences, K, is also 10. Using the formula, we get 0.00614. A very small likelihood we will find the best 10 out of a sample of 20 from a population of 30. Because there are so many discrete distributions, it can often be difficult to determine which distribution applies to which situation. Consider these guidelines. First, are we considering a rate per unit area or time without bound? If so, Poisson is likely going to be our best choice. If not, consider the second guideline. Are the number of trials fixed? If not, and there is a fixed number of successes, with the number of trials being the random variable, then either use the geometric or negative binomial distributions. If the number of trials is fixed, consider this guideline. If the probability of success is the same on all trials, then we want the binomial. If the probability of success is not the same on all trials, then consider the hypergeometric. This table will be helpful in making your choice.